Right, so what we've agreed with only 4 coders and 4 mentors, including myself, is that we will continue today, start looking at security. We're going to talk about cryptography, and then next week the 29th will be the final session of content, of new content, and then after that anything will just be guest talks from whoever wants to do them. So the 29th will probably look at authentication and authorization using Thomas's updated web app. But today we'll just talk about cryptography and the basics of security as I see it. Okay, let me kill the calendar. Okay, and let me, okay, so how do I want to start this? So, interesting enough today, this is my first time ever giving a talk on security. Security is not my forte. It's not, I don't find it particularly interesting. It's a necessity for me. It's absolute necessity, and it's of absolute necessity, especially in this modern world. So bear with me. As I said, this is my first time ever talking about security. But like I said, I'm a computer scientist, and being a computer scientist means that you have an appreciation of what we call the gamut of computer science. That's what that means, is the entire subject base. If I'm not a specialist, I have an awareness of it. Right, let's begin. So as I was saying, my first time ever talking about security. Won't this be an interesting state of affairs? So security. So you're all probably very familiar with security from the terms of, things like, I'm going to take a guess here, viruses, malware, spyware. Lots of you keep telling me things like, oh, Michael, don't DDoS my server. Attacks like that. But security as a topic is far richer than those things. And in fact, we're not going to be talking about those things at all. In my view, computer software like viruses or malware or whatever, all of them are just forms of malicious programs. They work in different ways, they do different things, but they're all just programs with malicious intent. They exploit you or take advantage of you in different ways. Most of you here, or all of you, can write Python code. You've looked at Python code. If you have the knowledge, there's nothing stopping you from writing viruses or malware or whatever else in a programming language of your choice and running it on somebody's computer, right? What's of real importance is how, from my point of view, is how do these threats get onto your computers in the first place? They say that, your computer is only safe as you are kind of cautious about what you put on your computer and what you give your computer access to. And there are many, many different mechanisms for keeping your computer safe. Additionally, the other big side of security is in terms of securing your computer, and in terms of what data goes in and out, and ensuring what I would call the trustworthiness of what goes in and out of your computer. Okay, so for example, if you download, say for example, a software program that you want to install on your computer, you might often be greeted with, in the installer, you might be greeted with a window that says, hey, would you like to install this browser plugin, this free browser plugin that will allow you to, download videos from video streaming websites? And you say, oh sure, it's ticked by default in the installer, and you're just, oh sure, I don't know anything about the piece of software, but yeah, it's ticked by default. I'm just gonna, why not? That sounds like a cool feature. And then you tick it, and then you have a piece of software of unknown origin, and you don't know whether you trust it or not, but you've just installed this on your computer. That kind of vigilance is important when it comes to security. So this question of trust, how do you know that you can trust someone or something or a piece of software? Okay, so there are different mechanisms for establishing the trust. For example, you're looking at my monitor here. All of you except Kyle can maybe see my screen. If I go to a website, like I'm going to go to www.ibm.com, and feel free to do this on your own computer. Pick your website of choice and go to it now. Right, now, as I was saying, I'm now on the IBM website, and I'm inviting all of you on the call this evening to go onto your favorite website. I don't know what web browser you're using, but I'm using Firefox. And if I look in the address bar at the top of the page, first thing I want to draw your attention to is the protocol. We talked about these in our networking sessions. Our protocol is HTTPS, right? Now let me put my participants window up so I can start asking you questions and see who puts their hands up. Can anybody? When I asked this before, and I wonder who remembers. Does anybody remember what? Well, let's drop the S for a moment. Does anybody remember what HTTP stands for? Feel free to raise your hand in WebEx. Okay, well, HTTP stands for Hypertext Transfer Protocol. And the S at the end here is the secure version of HTTP. Okay, so we're using a secure protocol to talk to the IBM server. When we put IBM.com into the address bar, we sent a GET HTTPS request over to the IBM server, and I've got back a web page. It looks like the IBM homepage. Yeah, it looks it, but how do I really know I'm talking to IBM? How do I know, for example, that someone hasn't spoofed this thing? Well, one of the ways I can determine that up in the address bar is by looking at the little padlock icon. If I click on that, it tells me I have a secure connection. So if I open that, it says you are securely connected to this site, and it says it's verified by DigiCert Inc. Now let me press more information there. If you go onto your favorite website, your site might also be verified, but it might not be verified by DigiCert. There's other authorities as well that will verify your site. What does it say though? It says the website is IBM.com, verified by DigiCert Inc. And it says something expires on the 7th of April, 2022. And it says here that I've established under the technical details, it says my connection is encrypted. Encrypted. So when we think about encryption, we're into this realm of cryptography. Okay, and we'll come back to that in a moment. That's what this is primarily about. Look at that. This is lovely actually, because this is what I want to talk about later on. Look at what it says in the brackets there. It says TLS, which is a form of secure connection, and it says AES 256. Just remember this for the moment. We're going to be seeing this later. AES 256. Okay. Now, expires on 7th of April 2022. It says there's a button here that says view certificates. Let's view the certificate. Here's the certificate. So what does it say? This is a certificate that proves the integrity and the ownership of this website. It says the subject of the certificate is about who it's about. It's issued to a company in the United States of America that's located in New York State. The locality is Armonk. Armonk is a town in New York State, or it's a small city, I'm not sure. That is where IBM HQ is, Armonk. I've been to IBM in New York on Madison Avenue, yeah, but I haven't been to Armonk, right? Organization is IBM, International Business Machines Corporation. If you didn't know that IBM stands for International Business Machines, now you do, okay? The name of the website is www.ibm.com, okay? Now, this certificate proving the authenticity of this IBM website is issued by a company in the US called, well, I should say an organization rather than company, an organization called DigiCert Inc., right? And they have their own certificate, right, which is this one here. And it says the certificate was granted to IBM on Monday, the 29th of March on 2021, and it will expire on Wednesday, the 6th of April, 2022. IBM's websites have lots of different other names that this certificate is also used for, such as IBM.com. Did I see there developer.ibm.com? I wonder is console.ibm.com there. I don't see that one. But these are lots of different websites that this certificate is for. They're all alternative names. That's what the ALT stands for here. And does anybody remember from the networking session what the DNS is? That's an open question. So DNS stands for Domain Name System. And if you remember, DNS is how we Dennis talked about it in his chat as well. DNS is how we translate an IP address to an actual website address. So remember, we were able to do a DNS lookup and find the IP address for the Coder Dojo website. And then we were able to use DNS to convert coderdojo.com into the IP address of the coderdojo.com. Now look at this. This certificate is signed, right? It's signed with a key, something called a public key. using an algorithm, and we talked about algorithms at the beginning of talk number 1, an algorithm called RSA, and we'll revisit this later as well. Everything else, we don't really care about right now. So we're using, so when you go onto the website, so again, I invite you all to open a website now in your browser, right? Find its certificates by clicking the little padlock icon and view information about the certificate, right? That will tell you something like, it's basically telling us that DigiCert has verified that this website is genuine and it belongs to IBM.com, and therefore they have granted the certificate. But what is the meaning of that? Unfortunately, Parag has just posed the question in the chat. Is DigiCert the only certificate company, or are there a couple of others? I've checked like 3 websites and they're all DigiCert. That's very good that you've asked that, Parag. So there are other companies. The other big company that I can think of off the top of my head is VeriSign. VeriSign is a global provider of domain name registry services. They will offer certificates, SSL certificate. That's what we were just looking at on the IBM website. So they will offer certificates. The other big company I can think of is called Let's Encrypt. We use a lot of these certs in our work, actually. Let's Encrypt will also give you certificates. So there you go. DigiCert, I think, is by far the most common, but there are other ones out there like VeriSign and Let's Encrypt. Okay. I think our product actually uses Let's Encrypt, but anyway. And the next point I was going to make, thank you, Parag, are they free or are they paid for? They are paid for, right? They are paid for. You must pay for them, right?
Not Let's Encrypt.
Huh?
Not with Let's Encrypt.
Let's Encrypt does free ones, but there's problems with that, right? But let's come back to that, okay? So Let's Encrypt will allow you to do it for free. That's why some of our products use them, right? Some of our products, for example, if you wanted to use a certificate that was not in our products, right? And I don't want to get into the technical details of the product. If somebody purchases our product out of the box, you will get a certificate that's signed by Let's Encrypt. If you want to get a certificate that's signed by something like VeriSign or DigiCert, you actually have to pay for it, right? You don't have to pay IBM. We provide support for you to provide your own custom certificate into our software. But it's up to you, the customer, to go away to DigiSign or go away to VeriSign or DigiCert and buy a certificate from them, and then load that certificate into your software with IBM, and that will then replace the Let's Encrypt certificate. Okay. Now, generally speaking, though, the problem with the Let's Encrypt certificate, right, is that not everybody trusts it out of the box. Okay. Your web browser, and let me move this over here a second. Now I haven't prepared this. Maybe I should have. Let's have a look in here. Your web browser, right, knows what certificate issuers it trusts. Okay. Now let me see here for a second. Let me see now. Can I privacy security? There must be a way how to figure this out. Oh yeah, view certificates. Oh, so these are all the certificates that this is my certificate manager. These are all certificates I've chosen to trust. Your certificates, authentication decisions, people, servers. Like, do you see a lot of these ones, for example? Do you see do you see these actually look, do you see these entries identify server certificate error exceptions? You see all these things here? These are development servers within IBM that I've deployed. You see my name and they're MOS, right? They're called Cert Manager certificates, right? And you see my web browser doesn't trust. Cert Manager is another thing then a bit like Let's Encrypt. My browser does not automatically trust Cert Manager, so I have to add an exception in my browser to say, yes, trust this certificate. Oh, here we go. This is it. This is perfect. Authorities. You have certificates on file that identify these certificate authorities. So these are all the certificate authorities that my Firefox web browser will trust out of the box. So there's lots of things in here I don't even know the name of. Affirm Trust, Amazon even, which is interesting. But if we come down here, there's DigiCert. So I didn't put that there. That was already in my browser when I downloaded it and installed it. So it trusts DigiCert, and it trusts VeriSign is in there as well, I'm sure. It trusts an IBM certificate as well. Oh, I know why that is. We'll get into that. There's VeriSign. Look, is there as well. So I didn't put these here. My browser trusts these authorities. So it sees that DigiSign is, or DigiCert is an authority, VeriSign is an authority. And what that means is, when I go onto a website that presents a certificate by DigiCert, I don't get any notification from my web browser. However, if I go onto a website where there's a certificate that's issued by a certificate authority that my Firefox web browser does not trust, it's not going to take me straight to the website. It's going to throw up a kind of a black screen here saying this connection is not secure, or this connection cannot be trusted. I'm sure some of you will have seen that before. It would be cool now if I could bring one up to show you. Perhaps I can, or can I? I don't think I can actually, because I had some servers I could have shown you, but actually no. Well, maybe I'll find a picture. Firefox untrusted certificate. If I could at least get a picture of what we're looking at. I'm sure you'll have seen this before.
Is that a self-signed cert?
Correct.
I can DM you a link to where we have a self-signed cert on that site.
Yeah, obviously it won't trust a self-signed cert either. So I could sign a certificate myself, guys, and say, yeah, I trust this, but that's called a self-signed cert. But my browser doesn't trust self-signed certs. I, Michael O'Sullivan, Dr. Mike, I'm not a certificate authority. Thank you. Yeah, I had when I hesitated there a moment ago.
Yeah.
I was thinking of NetSoc.
Wow.
I said I wouldn't go there.
That time was your browser's fault.
My browser's fault. Okay. yeah. Okay, you're right, Thomas. Of course. Here we go. So this is a NetSoc server. NetSoc is like the networking society, as in video gaming society in UCC, of which Thomas is a member. And this is one of their servers. Control.netsoc.co port 8006. Now look at this, guys. We're trying to go to this thing and talk using HTTPS, right? Now, if we're using HTTPS rather than HTTP, it means there's a certificate involved, right? I am looking, nice one, kidding. That's right, Google certificate is from Google. Right, but actually my browser, I believe, trusts Google as a certificate issuer. Anyway, I said go to HTTPS. I expect a certificate. So part of the HTTPS protocol is when my web browser establishes a connection to the NetSoc server, which is probably in a machine somewhere in UCC. Is it, Thomas? Or is it in someone's house?
Yeah, it's in CloudKicks in Cork.
It's
on a server. It's in a data center.
Okay, it's in a data center. Okay, it's in a data center that I don't know. Okay, so when I send a HTTPS request to NetSoc, I'm being presented with a certificate back, but my browser is flagging a problem. So warning, potential security risk ahead. Firefox detected a potential security threat and did not continue to the website. So this is very important, guys. If you are visiting a website where your browser doesn't trust the certificates, you should be very hesitant about putting information like passwords and emails and credit card details into that website. Now, look what it says. What can you do about it? The issue is most likely with the website, and there's nothing you can do about it, which is true. So what's the problem? What is the problem here? Look up at the padlock in the address bar. It now says not secure, unlike IBM.com or draw.io where I was earlier. This is another one, actually. What's this? Oh, look at that, guys. There's another one. Cloudflare Inc. I know what Cloudflare is, of course. Here we go. Site information for control.netsoc.co. Connection not secure. So why is it not secure? You are not securely connected to the website. More information. Back to the general tab. No, sorry. Right. Website identity. Control.netsoc.co. Verified by PVE Cluster Manager CA. Now, Thomas, why did you tell us what in God's name that is?
That's Proxmox. It makes virtual machines and containers.
So it's a piece of software that you can use to create virtualized operating systems and containers, like the app I was running on the IBM cloud a few weeks ago. So that piece of software has signed this certificate. And PVE Cluster Manager, CA, is not in Firefox's list of trusted authorities. You see the word CA there, guys. CA stands for Certificate Authority. That's technically what DigiSign and VeriSign are, etc. So Thomas's software has its own certificate authority, and it's signed the certificate, and Firefox doesn't trust it. It expires on 21st of January 2022. Let's look at the cert. Oh, there we go. There's exactly what Thomas just said. The subject name, organizational, down here, the issuer name, common name, Proxmox virtual environment, organizational unit, whatever that ID is, an organization is PVE Cluster Management CA. Has a couple of alternative names, 127.0.0.1, interesting, Thomas. It's trying to use a public key certificate. We won't talk about that just yet. Yeah, so my browser does not trust this certificate at all for legit reasons. Although I trust Thomas. Or do I? Do I trust Thomas? That's what this particular talk is all about, right? Because we haven't got on to what I wanted to talk about today yet. So think about that question. Do I trust Thomas? We'll come back to that. Okay. Well, in reality, I do trust Thomas. What I'll do is I will say advanced. And what I'm going to do is, you can see the error code there. Security error, unknown issuer. That's that PVE cluster manager. It doesn't know who that is, but I'm going to choose to trust Thomas. And if all hell breaks loose, this is safe, Thomas, I assume, is it? I should probably ask.
Yeah.
Okay. Accept the risk and continue.
There's a login page that
Very good.
I'm not going to tell you the login for.
We don't need to log in here, but now we are on the website that we were trying to get to in the first place. So look at the address bar now. The not secure message has gone away, but it is replaced by a little exclamation mark reminding us that the connection is not secure. And look what I've done. You have added a security exception for this site. So if I go into my settings now, settings, go back to security, go down to certificates. Oh, geez, what have I done there? Visa certificates. Your certificates, not that one. I think people. Where is it? People. Oh, there should be. Oh yeah. Oh, there. No, these errors. Oh yeah, these are the ones. So these are the ones I've added exceptions for. So I don't know what order that is in now. Is it at the bottom? No, it's not. Anyway, there'll be an entry. I've loads of things. I do a lot of work. So oh, there it is. Yeah, nicely spotted. You see my name in some of these things here. MOS Michael Sullivan, my colleague CT Chris Toomey, our service that we work on. Control.netsoft.co port 806. So there's a permanent exception in there. I could remove it, but I'll leave it in there for now because I trust Thomas. There we go. So even browsing the web, my friends, is a question of trust. And what servers do I choose to trust? Okay, and I'm trusting Thomas in this case. But out of the box, your web server, or sorry, your web browser, Firefox or Chrome or Edge or Internet Explorer, is going to trust certain certificates that are signed by specific certificate authorities like DigiCert or VeriSign or Cloudflare or whatever, or Google even, right? It'll trust them, and therefore when we go to them, it's not going to issue any warnings or anything like this because our browser trusts them. Okay. Now you were talking about Let's Encrypt. I don't think the reason about this is I'm not sure. I can't remember. Does my browser have an inbuilt rule to trust Let's Encrypt certificates? But it goes back to Pari's question. How much do they cost? Well, you can get them for free for Let's Encrypt, which is why they're widely used in software development and industry. But if you were to go on to DigiSign, let's have a look. DigiSign, or sorry, DigiCert, I beg your pardon. DigiCert. Now, hopefully, guys, here will demonstrate to you why is it that Thomas's NetSoft server does not have one of these certificates. Let's see, basic SSL. Base price $238, multi-year plan or 3-year plan. Basic certificates. Now, yeah, what do we want? Secure Site Pro, is that this one? Oh yeah. Let's go to the enterprise one because we need enterprise ones for a big company like IBM. Warranty $2 million. Basic price $1,499. A certificate like this wouldn't do for IBM. IBM, well, big companies, SSL certificates cost in the manner of $20,000 a year. So that's why in development we tend to use free certificates, you know, and this is also why we ask customers to provide their own certificates for their software, because we don't ship them for free because they're pricey. So there we go. What's the warranty for? I suspect, I don't know the answer to that part. I suspect that the warranty is something to do with what happens if the certificate becomes compromised. Somebody could spoof the certificates, in which case the certificate would need to be regenerated. Or the certificate could be stolen, which could be used for phishing purposes, right? In any of these cases, the certificates would need to be regenerated. And in a big company, there's big, massive insurance concerns over those things. Like, can you imagine now? Let's go to google.com. Think about the world as we know it. If the certificate that was assigned to google.com was compromised in the next 30 minutes, meaning that nobody could access Google, because that's exactly what would happen, what do you think would happen to the world? Google owns things like YouTube and Gmail and everything. So these certificates are very, very important, right? It's very important that they're securely stored and they're not compromised or leaked in any way. That's probably why the warranty is there. That's why the warranty is so expensive. If something goes wrong with the certificate, immediate action needs to be taken to revoke the certificate that's been compromised, because that can be done. You can revoke the certificates and then issue a new certificate, right? But there would be massive disruption because of that. So that's why the warranty is in place, I would imagine. So we're talking big business here, guys. Big business, okay? Any other questions for me before we move on? So the next time you browse the web, have a think about what servers you're talking to and how are they proving to you that they're really who they say they are. Okay, if there's no questions, now that we understand, well, trust is important, what I want to talk about now is cryptography. Those certificates we saw, let's bring up the IBM certificate here again. Remember this. Connection secure, more information, go to the certificate. The certificate is signed with a key, right? And oh, Parag, you have another question. How can the website set? Oh, Jesus. How can the let me see now. How can the website send the certificate without it being compromised? How does the receiver get the certificate and not be able to copy it or steal it? Anybody could. Well, okay. That's a very good question, and it comes into what we're just about to talk about here. The certificate is encrypted using an algorithm, in this case called RSA, right? So I actually can't see the certificate. I can't see let me rephrase. You're probably thinking, but Michael, you're looking at the certificate right here in your web browser. I'm not looking at the certificate at all. I'm looking at information about the certificate. This is public information about the certificate that I'm allowed to see. The certificate itself is encrypted. I can't see the certificate. But if somebody was able to decrypt the certificate somehow, this is right. That's when it can be stolen, right? And to prevent the certificate from being decrypted, you use cryptography. Okay, and that's exactly what we're going to talk about now. So another very fortunately timed question, Park. Okay, so this certificate is encrypted, right? So again, cryptography. So let's have a look at that. Okay, I'm going to close this, and what I want to do is I want to talk about. I want to pose another question to you. Okay, now. Let's look at our WebEx meeting here for a moment. I think cryptography comes down to issues of trust. Okay, there's 10 of us on this WebEx call this evening. I can see Alan, I can see Killian, I can see Connor. Welcome, Connor. Jake and Kyle and Luca Forder and Parag and Thomas. It's a pity Niall isn't here. This would have been a good example, right? But it doesn't matter, right? How do I know? Oh, that's no worries, Parag. Let's go with that example for a second, right? Even if Niall's not here. Let's say Niall and Parag, right? They both live in the same house. Unlike all of you, you're all, the rest of you are different cause. What's to stop, for example, like Porrig is there now telling us that Niall is sick, so this is obviously not Niall. How do I know that this isn't Niall pretending to be Porrig and Porrig is the one who's sick? They're both in the same house, so it's technically possible. Does anybody have any
I'm still not convinced that they're not the same person and one of them's just really good at robotics.
Perhaps. One of them could be an android, I guess. Boss, my question stands. How do I know that that's really Porrig and that's not Niall pretending to be Porrig? Well, there's a very simple answer. I don't. Porrig is now telling us that he's Niall. I trust them, so I'm pretty sure it is Porrig. But the question is, Porrig is there telling me that he's Niall, and I suspect he's really Porrig, but he could be Niall, right? They're both in the same house, so there's no reason they couldn't swap laptops or something, right? The answer is nothing. There's nothing I can do to prove that Porrig here is actually Niall. I'm trusting Porrig because I know all of you in person from the dojo that they wouldn't lie to me, and that is Porrig, right? But that's not verifying that. That's me saying, oh, it's likely that really is Porrig. And he's
It would actually be really funny if they switched.
It would, but they might have to do it sometime. But we're at the end of these sessions now, so they won't have a chance. But yeah, there's no way I can tell, really, bar, I don't know, turning on the webcam or something and seeing something about them that proves that that's really Porrig, except they're identical twins. So that doesn't really prove anything either, I guess. So I can't. Likewise, all of you, the rest of you on this call, I can't really prove that all of you are who you say you are. Let's see, I've heard Alan speak. I haven't heard Killian speak. I haven't heard Connor or Jake speak or Luca. I've heard Kyle speak. I've heard Luca Forder speak. I haven't
forget it.
Huh? What was that?
Don't you forget? Don't you forget it?
Right. And I've heard Thomas speak. So I'm pretty sure Thomas, for example, is Thomas. He was talking about the NetSock server, right? But for those of you who haven't spoken yet, I don't really know any of you is really you. All right. So I can't verify that all of you are really who you say you are. So if I can't verify you are all who you say you are, how can I really trust you? Okay. So think about that when you're thinking about verification, okay? Because what we're going to be talking about when it comes to cryptography is verification and integrity, okay? Now, what I want to talk to you about is a very simple scenario, and I shouldn't have brought this up because I spoiled what I'm going to talk about. Let's say I want to send a message to one of you. Let's say I want to send a message to let's say Thomas, right? Let's say Thomas took us to the that NetSock server a while ago, and it took us to a page that asked for a username and a password. Okay. Let's say let's say that Thomas wanted to send me the password to that server, but he doesn't want any of you to see it. Can anybody suggest what Thomas might do? Hands up or anything.
Private message you.
He could private message me. It's true. Any Connor? Oh, I think your mic is off, Connor. I can see you unmuted, but we can't hear anything. So check your audio again.
What's that?
Oh, we hear you now, Connor. We hear you now, Connor. Welcome. Oh, I think we've lost you again now, Connor.
I have to use my laptop mic, but you can send him a letter.
That's okay. I can hear you now. And go on, yeah, I can hear you.
You can send. You can send a letter.
I should what? What should I do? Send a letter.
Never mind.
Oh yes, I could. I could post a letter. Yeah, I could post a letter. Or sorry, Thomas could post me a letter with the password. So that's true. So yeah, he could directly message me. He could post me a letter. And what he could not do for Porrig, send this in a cipher. Thank you. That was the answer I was looking for. So he could send this in a cipher. right? That means that Thomas could send me the password in an encrypted fashion, in a way that only I could understand, only I could decipher it. Okay, that none of you. So if, for example, and I'm gonna let me pretend the password is Michael, right? If I send that into the chat, you can all see it and you can all understand it. But what if I was to send a message to Thomas, like, I don't know, oh geez, I don't know, I'm desperate at coming up with things in the spur of the moment. I don't know, Connor.
You have to do it with like the letters of the alphabet in order of the letters in your name, like 1, 2, 3, 4, 5. For like 1 for A.
Oh, that's very interesting. Oh, okay, I got you. Very, very good, excellent suggestion, Connor. So I could send him the letter. So if the password was Michael, so I think M is 13 in the alphabet. I is, oh geez, I don't know. I'm like A, B, C, D, E, F, G, H, I. That's an extra 9. C is 1, 2, 3. H, A, B, C, D, E, F, G, H is 8. A is 1, E is 5, isn't it? A, B, C, D, E, no, oh yeah, 5. And then L will be 1 before M, so it's 12. So I could send that to him. That's true. I could send that to him. I could send him those numbers, and Thomas would know, oh, Michael is sending me the number, as Connor said, is sending me the numbers of the letters in the alphabet. So M is the 13th letter in the alphabet, I is the 9th letter in the alphabet, and so on. So Thomas could decrypt the numbers. He could match up those numbers to the letters and say, oh yeah, he means Michael, that's the password. But Power, yeah, it's an inconspicuous message. The problem with that is it's a fairly obvious thing that could easily be broken, right? So we need to come up with a secure cipher. So, but very good, Connor. I'm delighted you brought up that example, because that's exactly what I want to start out with, right? So that's one scheme. I could just put in the numbers of letters in the alphabet. Here's another very famous one. It's known as the Caesar Cipher. Well, not that one. This one. I could switch the letters in the alphabet somewhat. So this is in olden times, apparently, how Julius Caesar's generals used to send messages to far off lands to their generals in the battlefield. They would write the message on paper, but what they would do is they would shift the letters. So for example, in this case, in this example here, they would shift the letter back 3 characters. So if they wanted to write something with the letter E, they'll go back 3 letters. 1, 2, 3, and you get a B. So instead of an E, they would write a B. So if I wanted to write Michael, I'd have, so what's, oh god, let me get the alphabet there, guys. Alphabet, which I thought was going to give me Google, and actually it has over here on the site. Alphabet is the parent owner of Google, guys, if you don't know. There we go. There's our letters, right? So let's see.
Alphabet's website is abc.xyz.
Is it? Oh, cool.
Yeah, it is, because alphabet.com was, of course, taken by the time they got a website for it.
Oh yeah, very good. Yeah. All right. What if you there's the letters? What if you had 2 lists and then a randomized one? We'll get to that once you finish the example. But let me just explain the Caesar Cipher. So if I was to go M and go 3 characters back, 1, 2, 3. So that's a J. I and go 3 characters back, 1, 2, 3. What is that? A B C D E F G. No, that's dreadful. Okay, let's do this one. So, oh goodness me. So M, 1, 2, 3. So J, and then I, 1, 2, 3, would be F. M I C, and go 3 letters back. Oh, if I go 3 letters back from C, I can't. If I go 3 letters back from C, I'm going on A. So what do I have to do? I actually have to go backwards. I have to go to the back of the alphabet. I have to go to Z. M-I-C-H, and go 3 letters back, that's E. A, I have to go 3 letters back through the alphabet again, that'll be X. E, if I go 3 letters back, I'll get B. And L, if I go 3 letters back, I'll get I. So there's Michael according to that version of the Caesar algorithm. All right, but it doesn't have to be 3 characters. I could go back 4 characters, or I could go forward 5 characters, whatever, you know. Pareg, you can you unmute yourself and can you explain what you're trying to describe to me there? I don't fully understand what you're proposing to me.
Okay, so my idea is, what if you had two alphabets, right? So one of them is just or two lists, sorry. One of them is the normal alphabet, and then one of them is it randomized.
Okay.
And then you had the message that you wanted to send to somebody. So you go through the message letter by letter, and you find the position of that letter in the randomized one.
Yeah.
And then you find the position that was in the other list.
Mm-hmm.
And then you send that letter, if that makes sense.
That's a great idea. That's a great idea. That would be much more difficult to break than the Caesar cipher, because the thing is with the Caesar cipher, if you figure out how many letters, if you figure out 1 or 2 or 3 letters, you'll probably be able to figure out all of them. Wouldn't be that hard. You've only 26 letters in your alphabet. With your randomized alphabet, the only way you could probably decrypt it is if you had your randomized list, right? So the risk of breaking the message would be if the leaked alphabet, the leaked randomized alphabet was somehow exposed to someone, right? Otherwise, it would be difficult because, yeah, in that idea, Parag, there'd be no discernible pattern of characters in your randomized list. That's a good idea. Very good idea. There's even more ways of doing it. Let me show you Lincolnshire culture. In spies, like the real life James Bond, they used to, like a bit like what Niall is describing. What Niall is describing essentially is something we would describe as something like what we would call a one-time pad. One-time pad. So this is very similar to what you're describing, Parag, right? One-time pad on Wikipedia. So this is an example of a one-time pad. See this picture here. See all these randomized letters of the alphabets, right? This is probably one pad, and it would be used for one message, and then after it's been used, it would be scrapped. And then you'd have to go to, you can see in the next picture here, there's a book. Each page is a randomized alphabet along the lines of what Parag was talking about. So they have a whole book of randomized alphabets. And the person they're sending the message to would know on what particular day or of the week or whatever, which page they should go to, such that if they received a message with randomized letters, they would be able to go to the correct page on the one-time pad and say, look, for character sequence 1, use the letters across the top to decipher. So I don't fully understand how they work. You can see there one is that if they receive an S, you should replace it with a T or something like that. And the thing about the Meal one-time pad is that if they got lost, the message could never, the one pad would never be reused, so it would be scrapped. Okay, so that minimized the risk of the alphabet being exposed to a malicious hacker or a malicious party who didn't want to know the message, right? The risk would be if they lost the book of the one-time pad. That would be awful. Now, here's an example of real-life James Bond. You look at James Bond films and you think, oh, aren't they fancy? Well, real-life spying is a bit more, was in the past, a bit more low-key, right? Real-life spies used to use something called number stations. Has anybody heard of a number station? No? Okay, well, number stations, it's a radio station. So you and I, Joe Blogs on the street, could actually tune into these broadcasts. And what this was, the Lincolnshire Poacher is a very famous example of what's called a number station. And you can see here the description on Wikipedia. The Lincolnshire Poacher was a British powerful shortwave number station that transmitted from Cyprus, where there's an RAF military airbase, from the mid-1960s to June 2008. The station gained its commonly known name as it uses bars from the English folk song, The Lincolnshire Poacher, as what's known as an interval signal. So you can see here, RAF Akwatiri, I can't say that word, Akwatiri, which is an air base on Cyprus. And for can't you tune into stations like this with AM instead of FM? It could be either, Parg. It could be AM or FM, I believe, as long as it's a shortwave radio station. You could tune into these things just like it's a radio in your car, and you can listen to them, and you can listen to the messages being sent to the spies. And our understanding of the Lincolnshire Poacher Station is it used to be used to communicate with British MI6 operatives operating in the Middle East during these years. These days, they don't use these things anymore, but for years, they were broadcast up until June 2008. And what they consisted of was something called an interval signal, which is usually a piece of music that identified who was sending the message, and then followed a series of numbers. And the spy would have to write down the numbers from the radio station and then use his one-time pad, like Parag suggested, to decipher his operating instructions from MI6 in London. And I'm going to play for you now. This is a real recording of the Lincolnshire Poacher, right? And there's loads of these on YouTube. Lots of different countries had their own number stations like this, but the Lincolnshire Poacher is by far the most famous one. I hope you can hear this now. If I play the video, minus the adverts.
People never believe how easy it is to make a square space.
Here we go. Let me know if you can hear this. So that song, that tune, is the English song called the Lincolnshire Poacher. So this is the identifier signal. And in a moment, you're going to hear the numbers being played to the spies, right? In a moment.
It's like a phone ringtone.
Oh, come on. Let's skip on the cover. Here you go.
39715. 39715.
So this woman's voice is reading out the encrypted message, right? And this message.
97115.
Now let me pause it a second. Nobody knows what the meaning of those numbers are, because first of all, we don't have the one-time pad, so we can't decipher what she's saying. She's also, you can hear there, she's repeating the numbers, was it 39715 over and over again. It's what's generally thought is that those numbers are identifying the spy, the operative that they want to communicate with. Okay, so the spy out in operation in the field somewhere would have to listen to the frequency, the radio frequency, at a particular time of the day that was previously agreed to listen for the messages, and then he'd have to know, you know, is that identifier 39715, is that really for me or someone else? You know, if the numbers actually change as it goes on. You can see it's 4 minutes long. Killian, so was anyone able to tune into this because of how encrypted it was? Anyone could tune into this. You could go into your car in the 80s and tune to this and listen to it like you listen to 2FM or 96FM today. And the beauty of it was it's perfectly secret, because unless you have the one-time pad, you have no way of knowing what the hell the message is about. As a documentary maker once put it, those numbers that you're listening to there, that's not a real woman talking, that's a machine speaking with a woman's voice. Those numbers, as the documentary maker said, could mean everything is perfectly fine or all hell is breaking loose. Those numbers, for example, could be the start of a nuclear war. They could be ordering the assassination of somebody. You never know. Oh, I don't. How do I get back to that? So yeah, it is pretty creepy, and lots of countries had their own ones, and you can Google them later on. The number stations on YouTube. There's Sorry now, guys. I'm after putting my thing into full screen. What have I done here? 1 second here, guys. Let me just fix my bloody monitor. There we go. Sure. Yeah, this one. Yeah. So there we go. As you move on.
397.
Right, here we go. And what you're going to hear now is there's another sound which denotes the end of one part of the message and the start of the next part of the message, which normally means they had to consult like the next paragraph or next sequence of numbers on their one-time pad.
Six, 4, 7, 5.
And then we got a whole different sequence of numbers.
4, 7, 5.
And then if we come to the end of it, I think. I think we'll just hear the ligature portal again. Some of them have different signals for denoting the end of the message. Yeah, so another very famous one was UVB76, which is still broadcasting today. It's a Russian one. It's known as the buzzer. That's probably it live, is it? Yeah, the buzzer. Do you hear the buzzing?
I can't hear it personally.
That's a Russian one, and they identified the exact building where that was being broadcast from. It got moved around. That's been broadcasting for 60 years, almost continuously, back from Soviet times. And there's recordings of that one as well, where they played numbers to operatives as well. So yeah, so fascinating stuff, all this cryptography stuff. But how does any of that pertain to us? What it means is we want a way to send messages without the risk of somebody else intercepting and receiving them, okay? Now, excuse me. So we've talked a bit about the Caesar Cipher, the one-time pad, Pari's algorithm of the randomized alphabet. We've looked at the number stations. There's a project called the Clone It project. I actually bought it several years ago. It's a CD. It's a 5 CDs. I actually own it. The Clone It project, recordings of shortwave number stations. This guy collected recordings of number stations from all over the world. Some of them are very freaky, very freaky. The ligature culture is almost a jolly one. So you can that's all. It's all on YouTube. It's very interesting to read up on. Anyway, so encrypting and decrypting messages using ciphers. Be it the Caesar Cipher, a one-time pad, a number station, whatever. We can do that in our code as well. Okay? And there's different algorithms for doing these things. Okay? Now, in each case, we use something called a key. We need a key to encrypt something, and we need a key to decrypt something. And there are two types of keys that we can use when we're talking about encryption. We've called symmetric keys and asymmetric keys. So for a symmetric key encryption algorithm, both the encryption and the decryption keys are the same. Okay? That's risky. Okay? Because it means if my key is exposed to someone who's not the intended party, again, I could, for example, if I wanted Thomas to send me that password, I could have said, here, Thomas, please encrypt the password with this particular key, with this particular encryption algorithm, and send me the encrypted text. Right? I can then use that same encryption key to decrypt Thomas's message and get the password to the server. But if I was to give the password, or sorry, if I was to give the encryption key to one of yourselves, Park or Killian or whoever, you could also decrypt Thomas's message. And we don't want that. That's not great, although it's very widely used. A better means is to use an asymmetric key, which is where the encryption and the decryption keys are different. And guess what? We've seen examples of them today already. We go back into the search for IBM. This certificate here, or sorry, this is the IBM certificate. This thing here, it says public key info, which is what's known as an asymmetric key algorithm, RSA. So that's an asymmetric key. Okay, so that certificate is encrypted with an asymmetric key. So this is why it's difficult to see it, Park. I know how to read. I don't have the key to decrypt the certificate, okay? But what Google does make available is the public key that it used to encrypt it, but I do not have the key to decrypt it, okay? Now, let's go back to Thomas's website. I noticed this earlier, I think, Thomas. Let's see. Back into the certificate. Oh, I'm right. Oh, no, you've got the RSA as well. I thought I saw another one earlier, but is it somewhere?
That's not the same certificate, that's a different one. I'm pretty sure there was an RSA.
I was looking for this RSA. I'm looking for AES, Thomas. I'm sure I saw an AES certificate somewhere. It might have been in my own exceptions anyway, because I work with some AES keys. Anyway, doesn't matter. Right, so let's have a look at some code before we finish up for the night. So, this is a Python program that uses an encryption algorithm with a symmetric key. And this is a very old encryption algorithm that's not widely used because it's considered to be so vulnerable now. This is called DES. Now, geez, I can't remember. I know ES stands for encryption standard, but I can't remember what DES stands for. Data encryption standard. Okay, DES. Okay. So in this Python program, I'm going to encrypt a string of data, which happens to be this message here. Subscribe to Bytes Travel, my ever glorious YouTube channel, which is only like 70 subscribers away from 1,000 subscribers. It will be a momentous day. So here's my message. Here's my message, and I want to encrypt that message using the DES encryption algorithm. To do that, I need a key. I need a key to encrypt that message. Oh, sorry, yeah, I should have mentioned this. You're probably wondering, what's the B? What's the B? So this now, so let me take out the B for a second. What type of data is this, my friends? This is a string. It's in double quotes, so that's a string. If I take out the B here, this is also a string, okay? Now, it's just correct, right? It's a string. So one slight complication here. To do this encryption, I'm using a Python module called PyDes. It implements the DES encryption algorithm, okay? And when you're using Python 3, which is what I'm using here, PyDes will not accept a string to encrypt. What you need to provide it are the bytes of a string. So to get in Python 3, to get the bytes of a string, I can put a B before it. Like that. So I can show you in Python here, look, Python 3. If I do name equals Michael and print name, I get Michael. Okay, now let's try this. Let's if I say name bytes, what are the computer bytes, i.e. like the ones and zeros that make up the string Michael? I can do B string Michael. And if I print name bytes, what I'm actually getting, you see, it's coming back with B Michael. It's giving me a what print will do is gives me a string representation of the contents of this variable. But this variable does not contain the string Michael. It contains the bytes that make up the string Michael. Okay, so PyDes in Python 3 requires you to provide the inputs in byte form rather than string form. So to do that, I just put a B in front of them, and that takes care of that. It's a Python 3 feature. Now, so here's the message I want to encrypt, right? Subscribe to Byte Travel. Now, what I need to do in DES is I need to provide a key that can be used with the DES algorithm to encrypt this message. And in DES, I need to provide an 8-byte key. I need to provide a key that is 8 bytes long, which is what this is actually. Michael J. Each character, M and I, so on, each character is 1 byte in length. So I have 8 characters in here, which is 8 bytes. Now, this kind of stuff is a bit complex, so we're not going to talk about all of this. This is a demonstration, okay? But here I am, I'm creating a cipher called crypto. And to do that, I'm using the DES module of PyDes. So I'm passing into DES here. I'm passing in the key that I want to use to encrypt the message, which is this, Michael J. Please ignore all of this. This is just well beyond the scope of what we want to talk about, but just I need to have these things in here, okay? I don't want to talk about padding or anything like that, okay? This has to do with where a message starts and ends when it's stored in memory, okay? That's beyond what we want to talk about today. Just take for granted that these are the recommended settings and they have to be there. So I'm creating a cipher with my key, Michael J. And I can use that cipher to then encrypt something. So I'm going to use that cipher to encrypt message, which is subscribed to byte travel. So that's going to use the DES algorithm with the key Michael J to encrypt the string bytes of the message subscribed to byte travel. It'll print it out, and then because it's a symmetric algorithm, I can decrypt the message with the same key. So I'm doing crypto.decrypt the encrypted message. Right, and then I'm asserting. Well, I will talk about what that is. Leave that over now. This is just making sure that the decrypted message is equal to the message that was not encrypted. Okay, now let me run that. I'm going to show you. Python 3. What's the thing called? DES crypt exam.py. There we go. Look at that now, guys. This here is the message subscribed to byte travel but encrypted. And these are, right? That's the encrypted message subscribed to byte travel. That's coming from this line here, line 7. Right? And then I'm decrypting it, and then you can see I'm printing out the decrypted message, which is subscribed to byte travel. So the decrypted message is equal to the original message, which is exactly what we would expect, because they're the same key. Okay? What if I was to do this? If I was to do another crypto 2 equals, and let's do this. Let me set up another cipher. And let's put another key in here. Key 2, that has to be 8 bytes long. So I will just say MICHAEL, I don't know, JK, which is the next letter after J. And let's put that in there, key 2. And what we're going to do is we're going to use crypto 2 to decrypt the message instead of crypto 1. Okay, and we're just going to assert that crypto 2, that the decryption of the message is equal to the original message. And I'll say that. Let's run that now. Well, that worked. Worked. Decrypted message equals crypto 2 decrypted message. I would have I tried this earlier with a different algorithm and it worked. It's very interesting, isn't it? I've established a second cipher with a different encryption key and it was still able to decrypt the message. That's bloody strange. I wonder is this why they don't use DES anymore? Anyway, I will figure out why that is and I will come back to you next week when we meet. But we don't use DES anymore because it's considered to be very weak. It's very easy to break an 8-bit or an 8-byte key, right? You could guess what the key is and decrypt the message. What I want to show you is a different algorithm, which is this one here, AES. AES is essentially the modern version of DES, an advanced encryption standard. This is now what's used by the American government to encrypt and decrypt things. It's another symmetric key algorithm. So the key for encrypting something is the same as the key for decrypting something. And I have a nice code sample here. And I'm going to run this and then we'll call it a day for the evening. Python 3, which is this AES string encrypt.py. Very good. Okay. Now, what I want to get to across to you today is two things: confidentiality and integrity. Okay, we need to know a bit about this for what Thomas is going to show us next week when he shows us the user's app that he's added the security to. Okay, encryption guarantees the confidentiality of a message. It's a way of guaranteeing kind of who the message has come from. Okay, but there's another measure which is integrity. Right? How can we guarantee, even if we can guarantee who is sending us the message and who is receiving the message by means of an encryption key that we both know, how do we guarantee that the message hasn't been tampered with, that nobody's interfered with the message while it was being sent? So one of you, I think Connor, I think you said it earlier, that Thomas could post me a letter with the password. But who's to say someone at the post office won't open that letter, tamper with this, and then send it to me, and then I'll receive it here and think that it's genuine? I can't really. We know Post opens our items, for example, for customs charges, but there's no way of knowing. So in computers, we want to be able to guarantee the integrity of something as well. And for that, we use something called a hash function. And Thomas touched on these last week when he was showing how he was hashing passwords. Right? So typically, we tend to do two things. We use encryption to guarantee the confidentiality of a message, and we use hashing to guarantee the integrity of a message. So let's have a look at this. This is another algorithm, a symmetric key algorithm for encrypting the message. AES, Advanced Encryption Standard. Now, AES, unlike DES, uses a minimum a 16-bit key. Sorry, 16-byte key. So here's the 16-byte key. It happens to have 16 characters in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And here's the message I want to send, and he's not here this evening to receive it. Secret message to be sent is, this is a secret message to Caleb. Hi. Here's the message I want to send to Caleb. Okay? And we can see that in the output here. Secret message to be sent is, this is a secret message to Caleb. Hi. So the first thing we do is we compute what's called the hash digest of the string to check. Well, it's a hashing algorithm. What it does is it provides a hexadecimal representation of the message, which is here. MD5 hash of the message is this. So using the MD5 hashing algorithm, we get this particular string here, this sequence of characters, that is essentially, this is a secret message to Caleb. Hi. That's what this is using an MD5 hash. That is a one-way hash. We talked about this a bit 2 weeks ago. I can't use the hash to encrypt the message. This MD5 is an algorithm for hashing pieces of data, and it's a one-way hash. Once it's been hashed, you can't unhash it. Okay? So I can't use the hashing alone to encrypt the message. This is why we use this just for integrity, and we use a different encryption algorithm to encrypt the message. So what we do then is we encrypt the message with AES. So we create another cipher, AES.new, and I'm using a Python module for this called Crypto. So we create a new AES cipher with our key, which is the 16-byte key. And then we also use something called a nonce, right? A nonce is a random string that's used to guarantee the uniqueness of the message, okay? If we didn't have a nonce, then it means somebody could replay the message in the future. And yes, Parg, a nonce is a bit like a salt, right? Except a nonce value is typically only used once, whereas a salt value could be reused again. So a nonce, for example, could be like the time in milliseconds. It guarantees uniqueness when if we didn't have the nonce in here, right, and the message is encrypted, if someone figured out the encryption key, they could send the same encrypted message a second time, right? And we'd have no way of knowing that the message has already been sent in the past. So a nonce will guarantee the uniqueness of a message. Basically, if I sent a message to a server and the message had included the nonce with it, and then I received a message again, with the same nonce, I will know that somebody is interfering with the communication because they've received the same nonce value twice. A nonce value can only be used once. That's what nonce actually stands for. N stands for number, and the rest of it is once. Number once. Number once. Okay? Now, we don't need to worry about that too much, right? I'm just explaining what has to be there in the code. So AES should really use a nonce, okay? Now, look what we're going to do. We're going to use the cipher to encrypt our message, which is, this is a secret message to Caleb. Hi. And the encrypted message is known as the cipher text. And we can see that down here. Encrypted message is this. There's the encrypted message. So I can then send that text over to Thomas or someone else who I want to receive this message securely. Now, on the other side, that was the first part of the program. The second part of the program is down here. How do we decrypt the message and guarantee its integrity? So I have to create a new cipher, but using the same key. So again, AES is a symmetric key algorithm. Both the sender and the receiver have to have the same key to encrypt and decrypt the message. And I also have to provide the same nonce as well. Now, then we can decrypt the message. Cipher Decryption.decrypt. So we decrypt the encrypted message, and we get back what's called the plain text. Once a particular cipher message has been decrypted, we say it is plain text. Okay? So I get the plain text back. And then what I do, remember, hashing is a one-way thing. If I want to guarantee the integrity of the message, I have to do an MD5 hash again on the decrypted message. So received MD5 hash equals hash library.md5 on the plain text. And we can see down here, MD5 hash of the received message is this string here. That's the same as the MD5 hash of the original message. And because they're the same, it means that the message has not been tampered with. The integrity is intact. Okay? And then finally, we get the decrypted message. Decrypted message is, this is a secret message to Caleb. Hi. So there we go. We've successfully decrypted the message with the same key. Only Thomas and I, for example, would have the key, so I can guarantee that it came from Thomas. The risk is the key could be exposed, but that's the risk we're taking with a symmetric key algorithm. And we've guaranteed the message as well. So look what I have here at the bottom. If the hash of the received message is equal to the hash of the original message, it means the message integrity is intact and it has not been tampered with. Otherwise, it has been tampered with. Let's have a demonstration of that, and then we'll call it a day. This is what I tried earlier, so this should work. Second key equals, we'll take 16-byte key from up here. And I'll misspell something like this, K. It's a 16-byte K, right? And I'll initialize my AES cipher with the second key. Second key. Now, so this cipher is now going to decrypt the message with a different key to that which it was encrypted with. Which is what the DES program is doing, but that didn't seem to mind. So let's see what happens here. So let's run that again. Oh, sorry guys, I made a small mistake. I made it a string rather than bytes, and you can see I'm getting the error here. Type string cannot be passed to C code. So I put a B in there. Whoops. So I put the B in here to make it a array of bytes, and I'll run that again. Right, let's have a look at this time, guys. Secret message to be sent is, this is a secret message to Caleb. Hi. And the MD5 hash of the message is this. The encrypted message is this. Now look at our decryption. The MD5 hash is now different of the received message. It's different to the original hash. And the decrypted message does not say, this is a secret message to Caleb. Hi. We've got a completely different message. It's indecipherable. This is the decrypted message. Therefore, the message integrity is not intact. It has been tampered with. So that demonstrates a symmetric key algorithm like AES. To decrypt something, we have to use the same encryption key that we used to encrypt the message in the first place, right? And in this case, the message has been tampered with because I didn't use the same key to decrypt the message. So that doesn't work, all right? So that's an illustration of encryption and decryption with AES, which is working as I expected it to. I don't know why the DES thing was okay. I'll have to have a look at that again. And I have other examples here that I won't walk through now. You can even encrypt files on your system, on your operating system with AES. I can encrypt a file. Write the encrypted message to a file on my system, and I can even, here's the encryption. I can write it to an encrypted file. The message subscribe to byte travel. Let's just run that. Python 3 AES file encrypt.py. So that's going to use an encryption key that says, I am so smart, Homer S. That's a quote from Homer Simpson. It's 16 bytes long. The message is subscribed to byte travel, and it's going to write it into a file called encrypted.bin. Let's have a look at my file system. There's the file encrypted.bin. If I show that file, it's all encrypted. I can't decipher these characters, but the decryption file, which is here, will open that file and decrypt it with the same key. Let's do that. So we're saying Python 3, this file is called AES file decrypt. Data is subscribed to byte travel. So that was able to decrypt the file and print out the message. Again, using the same key. It's a symmetric key algorithm. Excellent. So there's cryptography in action for you. But you can see the obvious vulnerability here. If that key is leaked to somebody, then anybody can decrypt the message. So that is why we much prefer to use asymmetric key algorithms, where the encryption and the decryption keys are different, right? Because if the key that was used to encrypt the message is leaked, then it's not a problem, because the decryption key is different. So an asymmetric algorithm is much more secure. And in fact, that nicely rounds us off. If we look at the certificate, the DigiCert certificate here on the IBM server, I said this earlier, but I'll say it again. An asymmetric algorithm for encryption is also known as a public key algorithm. And the most commonly used one is an algorithm called RSA. It's the most common asymmetric key algorithm you'll find out there. So this certificate is encrypted with an asymmetric key, which is why I cannot decode the certificate. I don't have the decryption key. So this is more secure than the AES algorithm, which is symmetric. So that's good, guys. We've seen some hashing functions in action, and we've seen some encryption and decryption in action with cryptography, all about establishing trust and integrity. On the web, we use certificates to guarantee the trust of the websites we're talking to. Spies have used number stations to securely transfer messages to their agents in the field. And we can use them in our code as well to decrypt messages. Any questions, my friends, on anything that we've seen tonight? Hands up, or feel free to write in the text chat. That was a lot, but that was a good introduction to cryptography, I think. Hopefully you've learned a lot from that this evening. Any questions at all? No? Okay. Oh, Connor, do you have your hand up? Go ahead, my friend.
Can you hear me?
Yep.
It's a bit unrelated, but is there a massive difference between a byte and a bit?
A byte is 8 bits.
Okay, thanks.
1 byte is equal to 8 bits. So this brings me on to another point which I'll make in a minute. So if I say like 3 in binary, which would be 0, 1, 1, right? 0, 1, 1. This is just Google's representation of it. So the length of this number is essentially 2 bits, right? 15 in binary. So to store the number 3, you could get away with using 2 bits, okay? But if I take 15 in binary, or it's not 15. Let's pick a number. Let's pick, like, I don't know. Let's go way up. There we go. 256 in binary. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 digits here, right? 8 bits, that's 1 bit, 2 bits, 2 bits, 3 bits, 4 bits, and so on. 1 byte is equal to 8 bits. So I couldn't store, this is telling me I couldn't store the number 256 in 1 byte. I need a little bit more than 1 byte. So 1 bit is equal to 8 bytes is the short answer to your question, Connor.
Thanks.
You're very welcome. Any other questions, guys? Okay, so I'll say this now to get this on the recording. As I mentioned, next week's session will be the final session. We'll finish off our look at security by looking at authentication and authorization using everything we've learned this evening. Okay, then we're done, aside from guest talks and whoever wants to give them. Okay, now at the very beginning of these sessions back in June, I had said that there was a few advanced topics we could look at that I excluded from these sessions because they're a bit more complicated and they might be a bit more boring over the WebEx. They're a bit less practical. But I wanted to offer all of you the opportunity for me to do a few more sessions on those topics. We could do them every second week or once a month or whatever. It doesn't even have to be every week. There'll probably be only maybe 3 or 4 more sessions on those. And those topics really are number systems, just like what Connor was asking, which is great that you brought up, Connor, like talking about binary number systems, hexadecimal number systems, octal number systems. How do we convert from a decimal number systems, of course, which is our own 1 to 10 number system? How do we do decimal to binary conversions, things like that? And the other thing I was considering having a session on, which I did at the dojo before, was the most complicated of all talks, which is on something called algorithm analysis, analyzing the performance and efficiency of an algorithm. Those two things are a bit mathematical, right? So I'm willing to do them with you if you want them. So think about it. No need for answers tonight. And then next week I will ask if people want to have those sessions. I mean, attendance is obviously dropping off now because school's back and other activities are on. We've a very small crowd tonight, so it might not even be worth it. But if there's some of you who want sessions to learn about binary numbers and how to analyze algorithms, I can do them. You just have to let me know, even if it's a smaller audience. The reason they're worth bringing up is because both binary number systems and algorithm analysis are both on the Leaving Cert Computer Science course. They're both on it. So if that's something you're interested in knowing about for that reason in the future, now might be a good time to have a look at them with me, and I'll try and keep it as simple as possible. All right? So think about it. I might send an email out about it, and I'll ask again about it next week. Parag, where can you actually get the comp sci course for the Leaving Cert? I will show you. You can see the sample papers and everything. It's not in my school. Yeah, you might be able to find somewhere else to take it somewhere else, Parag, and then do the exam in your school. Like in my school, they didn't teach agricultural science, so people went to other colleges to do it, but took the Leaving Cert agricultural science exam in my school. Leaving Cert computer science. So for that, what you really want to look at is examinations.ie. The State Examinations Commission, which do the Leaving Cert and the Junior Cert. If any of you are going to 3rd year of Junior Cert, you're going to be looking at this website a lot this year. But we'll look at the Leaving Cert one for the moment. Well, it's beyond all of you at the moment, a few years away from me, but just to show you. In here, you can find the syllabus. Why can't I see the syllabus there unless it's just a different name? If you're not interested in this, you can drop off and say thank you very much for attending, guys, and same time next week. Is it curriculum online? I've read the PDF of this before, so computer science. Do you specify video? I thought it was here a minute ago. Leaving Cert. Oh yeah, this is it. So there's our curriculum. So, I mean, you can read through this if you want, but this tells you what you study. You asked about like the section, there's the tree, they're divided up into 3 sections. Strand 1, practices and principles. Computer societies, computational thinking, design and development. And then 2 core concepts, abstraction, algorithms, computer systems, data. That's the other thing, data structures. Algorithm analysis falls under this guy, algorithms. I can send the link around to all this, but there's something I want to show you. The outcomes here, outcomes. This is what you're interested in, right? Computational thinking, problem solving, logical thinking, arithmetic thinking. So this is all like binary conversions and things like that. Logic skills. We've talked about Boolean logic. Explain the operation of a variety of algorithms. So we've looked at algorithms. Develop algorithms to implement chosen solutions. This is something we didn't do a lot because we didn't do a lot of we didn't really look at the assignments or the programming exercises I set. Let me see what I want to show you. Core concepts. Here we go. Here we go. Algorithms, programming concepts, sorting. These are all different sorting algorithms. And this is what I'd be talking about if we were to talk about the algorithm analysis. When we talk about algorithm analysis, we're talking about algorithmic complexity, which is, here we go, explain the common measures of algorithmic efficiency using any algorithm studied. So this is what I'd be talking about if we were to do that. And in bold means it's for higher level only, whereas not bold is common to ordinary level and higher level. Computer systems, CPU, registers, program counter, memory. I've talked about some of those things, but not all of them. Web network protocols, HTTP. We talked about. I didn't talk about TCP. We talked about IP. Didn't talk about VoIP. So I left a lot. I did a lot of these things at the dojo in person, but I left them out of this virtual classes because they're not so good over WebEx. I think they'd be a bit more boring. Relational databases. Things like that. So we've looked at a lot of these things already, right? So there's the syllabus, and then what I suggest you do is come back to State Examinations Commission and look at a sample paper down the bottom here. We'll go higher level. Sample paper, higher level, section A and B. This is what you have to actually sit. This is done. This is a written exam. Section A and B are written. Section C is all programming in Python or JavaScript. You do that on a computer, I understand it. So we've done some of these things already. Evaluate these Boolean expressions. Are they true and false? So 7 greater than 5, that's true. 7 greater than 5 and false. This is true, that's false. This is logical and, so that whole statement is false. So we've done all this, right? Add the 2 binary numbers. We haven't done that, but it's something I would show you. Convert your answer to decimal base 10. That's exactly what I'm talking about, number systems. There's a logical circuit. That's a NOT gate. That's an AND gate. Complete the truth table. Those were all in the exercises I set. What does this mystery function do? I'll tell you now. I think that's a mystery. That's a factorial function. It's a recursive function. We didn't talk about those. Improve this function. Here's some HTML. Sketch what the HTML would look like in your web browser. So there you go. Look what is meant by relational database. We talked about MySQL. We talked about primary keys in databases. Nice picture of a robot. Anyway, section B is all about computers and society, I think. And then we talked about this. We talked about the CPU. We talked about primary storage, RAM, auxiliary, secondary storage, like your hard drive or a CD-ROM, etc. I'm very impressed with all the things we talked about, guys, that are all on here. And then section C, I think you do in a computer. This is the actual programming to write Python code. So in this case, you have to, what do you do? The program, here's some code, is designed to calculate and display the BMI for a person. A sample run of the program is displayed below. If you enter 90 kilograms, you get a BMI of 27/7. Modify the program to do the following. Insert a comment, not boring. Currently in the program, the value of the variable height is hard-coded to 180. Modify the program so that it prompts the user to enter the value of height. The value should be converted to an integer. We did this to use the input function. And we know that the input function takes in all data as strings, and you can use the int function to convert the string to an int. So, you know, you guys have a great head up, my friends. So there you go. So I'll send that information on. You can be having a look at it. So number systems and algorithm analysis, and maybe data structures is the other thing I'd be proposing. So let me know, have a think about it. Killian, so would encryptions with keys not work unless you can give the key to someone in person, because you wouldn't be able to encrypt a key sending it to someone? I think what you're asking, Killian, is that for someone to decrypt something in a symmetric key algorithm, the other person has to have the key. Otherwise, it wouldn't work. That's correct. Unless the intended person has the key, it's pointless. That is true. All right. Any other questions, guys? Feel free to unmute yourself and ask the question. Might be quicker than typing. No? Okay. We will leave it at that. So, my friends, thank you all for joining. Again, I hope you found it interesting. And I'll make the code available on GitHub so you can tamper with some of that cryptography code yourselves to your heart's content. And next week, we'll finish off the whole thing by talking about authorization and authentication with Thomas's help. All right. Thank you all, guys. I'll stop the recording, and I will see you all next Wednesday at the same. I'll see you all next Wednesday at the same time.
Sounds good.
Guys, and have a good evening.
Thanks, Michael.
My pleasure, guys.
Thanks. Bye bye.
Bye.
Thanks.